What if I told you there's something lurking in the cosmic shadows, objects so strange they blur the line between planet and star? These celestial misfits are called brown dwarfs, and they're the universe's greatest underachievers. Picture a star that never quite made it, too massive to be a planet but too small to ignite the nuclear fires that light up true stars. They're the cosmic equivalent of a car stuck in neutral, full of potential but forever stalled. Yet, it's this very failure that makes them fascinating. Brown dwarfs defy categorization, and their bizarre behaviors have astronomers scratching their heads in equal parts confusion and wonder. Imagine a world where the sky glows a dull red, not from a sun but from a dim, smoldering orb that barely clings to stardom. Some brown dwarfs rage with storms more violent than Jupiter's great red spot, while others drift through space almost invisibly, emitting faint whispers of heat. Then there are the real oddballs, those that rain molten iron or harbor auroras so bright they outshine anything in our solar system. These aren't just failed stars, they're cosmic laboratories where the laws of physics play out in ways we're only beginning to understand. So why should we care about these celestial misfits? Because brown dwarfs hold secrets that could rewrite what we know about how stars and planets form. They challenge our definitions, surprise us with their quirks, and might even hold clues about the search for life beyond Earth. Over the next few minutes, we'll dive into 30 of their strangest behaviors, from mysterious radio signals to rogue dwarfs hurtling through space alone. Buckle up, because the universe is about to get a lot weirder. One of the most baffling quirks of brown dwarfs is their refusal to follow the cosmic rulebook when it comes to temperature. Unlike stars, which burn steadily thanks to nuclear fusion, or planets, which cool predictably over time, brown dwarfs behave like moody celestial teenagers, heating up and cooling down without warning. One day, they might flare unexpectedly, radiating surprising warmth, and the next, they could plummet into a chilly slump. Scientists first noticed this erratic behavior when tracking infrared emissions and found wild swings that no existing model could fully explain. So what's behind these temperature tantrums? One leading theory points to powerful magnetic fields twisting and snapping like rubber bands, generating bursts of heat. Another idea suggests hidden layers of energy deep within their atmospheres, pockets of turbulent gas, or even chemical reactions we don't fully understand yet. Then there's the possibility of gravitational squeezing, where the brown dwarf's own weight creates friction, sporadically warming its core. It's like squeezing a stress ball until it heats up in your hand, except this stress ball is a cosmic object dozens of times more massive than Jupiter. The strangest part, some brown dwarfs seem to defy age expectations entirely. Younger ones, which should theoretically be warmer, sometimes cool faster than anticipated, while older ones occasionally spike in temperature for no apparent reason. This unpredictability makes them incredibly frustrating and thrilling to study. Every time astronomers think they've pinned down a pattern, another brown dwarf breaks the rules all over again. If these cosmic rebels have taught us anything, it's that the universe loves a good plot twist. If you thought Earth's weather was unpredictable, wait until you hear about the alien skies of brown dwarfs. These cosmic oddballs don't just have clouds, they have clouds made of materials that would seem more at home in a blacksmith's furnace or a desert storm. Imagine entire atmospheres where it rains molten iron, or where gritty silicate particles swirl like interstellar sandstorms. Unlike the water vapor clouds of Earth or the ammonia-filled bands of Jupiter, brown dwarf clouds are forged in temperatures so extreme they turn familiar substances into something utterly alien. Take the case of one particularly strange brown dwarf, known to astronomers as Lumen 16a. Observations revealed its upper atmosphere is laced with clouds of liquid iron droplets, condensing and falling like metallic rain. But here's where it gets even weirder. These clouds don't blanket the entire object uniformly. Instead, they clump into patches and bands, creating swirling storms that rage for decades. Some scientists compare the view from below to a nightmarish version of Jupiter's Great Red Spot. Only instead of ammonia crystals, the winds whip scalding iron vapor across the sky. Then there are the sand clouds. On cooler brown dwarfs, temperatures drop just enough for silicates, essentially tiny grains of rock, to condense into thick, churning hazes. These particles don't behave like Earth's gentle raindrops. They collide and shatter, creating violent electric storms or even glassy showers. The weather systems are so chaotic that some brown dwarfs exhibit cloud avalanches, where entire layers of atmosphere suddenly collapse under the weight of accumulated sand-like particles. It's as if the sky itself has a breaking point. What makes these clouds so dynamic? The answer lies in the turbulent atmospheres of brown dwarfs, where gravity and heat create constant upheaval. With no solid surface to disrupt airflow, storms can spiral for centuries, and temperature gradients sharper than anything in our solar system fuel winds that scream at hurricane speeds. Unlike stars, which are too hot for clouds to form, or planets, which are usually too cold for exotic materials to vaporize, brown dwarfs occupy a Goldilocks zone of cosmic chaos. Their skies are laboratories for weather patterns we can't replicate anywhere else. And just when researchers think they've seen it all, new discoveries upend expectations. Recent infrared scans revealed a brown dwarf with patchy, discontinuous clouds that vanish and reappear in months, a phenomenon astronomers jokingly call cosmic bald spots. Whether it's molten metal storms or sandblasting winds, one thing's clear: the skies of these failed stars are rewriting the rules of planetary science, one bizarre cloud at a time. While brown dwarfs often lurk in darkness, some announce their presence with bursts of radio waves so powerful they outshine entire stars. This bizarre behavior defies expectations. Objects this small shouldn't produce such intense signals. Yet here they are, crackling like celestial walkie-talkies with emissions that can be detected across interstellar distances. Take the case of BDRJ 1750 plus 3809. A rogue brown dwarf discovered not by its faint glow but by its booming radio voice. It's like finding a whisper in a crowded room, only to realize the whisper is actually a shout. What's fueling these mysterious broadcasts? The answer lies in magnetic chaos. Brown dwarfs generate magnetic fields thousands of times stronger than Jupiter's, twisting and snapping like rubber bands stretched to their limits. When these fields reconnect, they unleash torrents of electrons spiraling at nearly light speed, a process that supercharges radio emissions. Imagine dragging your feet on a carpet, then touching a doorknob and getting a shock. Now scale that up to cosmic proportions, with magnetic discharges so violent they light up entire bands of the radio spectrum. Even weirder, some of these emissions pulse with clockwork regularity. The brown dwarf, nicknamed the Repeater, fires off radio bursts every 1.4 hours like a celestial lighthouse. Astronomers suspect these rhythms come from interactions between the dwarf's magnetic field and charged particles trapped in its atmosphere, a dance so precise it rivals the timing of pulsars, the universe's most accurate natural clocks. But the real head-scratcher is why only certain brown dwarfs do this. Magnetic activity typically fades as objects cool, yet some older brown dwarfs suddenly flare up with radio bursts after centuries of silence. It's as if these cosmic retirees get a second wind, defying all predictions. Whether it's hidden dynamos deep in their cores or interactions with unseen companions, one thing's certain: when a brown dwarf decides to sing, the entire galaxy can hear it. Just when astronomers think they've figured out brown dwarfs out, these cosmic underdogs throw another curveball: sudden, dramatic swings in brightness that can appear and vanish in hours. Unlike the predictable flicker of stars or the steady glow of planets, these variations are so extreme they've been mistaken for technical glitches. 1 minute, a brown dwarf might sit quietly in telescope data, barely registering. The next, it flares with the intensity of a stellar explosion, brightening by 10% or more before fading back into obscurity. What's behind these cosmic light shows? For some brown dwarfs, the culprit appears to be auroras on a scale that dwarfs Earth's northern lights. Charged particles, whipped into frenzy by powerful magnetic fields, collide with atmospheric gases, triggering dazzling displays that can outshine the dwarf's own thermal glow. But unlike planetary auroras, which require solar wind, brown dwarfs seem to generate these outbursts internally, like a self-sustaining neon sign in the void. The strangest part, some of these flares emit polarized light, spiraling through space like a corkscrew, suggesting magnetic fields so twisted they warp the very light escaping them. Then there are the dimming events, brown dwarfs that abruptly fade as if a cosmic hand turned a dial. Infrared observations of one object, WISEP J 190,648, 47 plus 401,106. 8, revealed patches of its atmosphere plunging into shadow without warning. The leading theory, titanic storms swirling with molten rock or metal vapors that temporarily blot out the underlying heat. Imagine hurricane clouds so thick they shroud an entire world, but instead of water, they're made of vaporized minerals condensing into eerie, high-altitude fog. The most baffling cases show both phenomena at once: wild brightening followed by abrupt dimming, as if the brown dwarf can't decide whether to reveal or hide itself. One particularly dramatic example, 2 mass J08251968 plus 2,115,521, brightened by 30% in visible light over 2 hours, then faded even faster, leaving astronomers scrambling for explanations. Could it be magnetic reconnection events similar to solar flares but compressed into a tighter, fiercer package? Or perhaps atmospheric shockwaves where supersonic winds collide and release bursts of energy like thunderous lightning? What makes these variations so tantalizing is their unpredictability. Unlike pulsating stars or eclipsing binary systems, brown dwarf brightness changes follow no discernible schedule. They're the cosmic equivalent of a mood ring shifting without warning, leaving scientists to decode what each hue might mean. And with every new observation, the mystery deepens, proving once again that in the realm of failed stars, expectation is the first rule to break. Most stars have companions, orbiting partners, or bustling solar systems to call home. But brown dwarfs, many are cosmic loners, drifting through the galaxy's dark corners without a single planet or star to keep them company. These solitary wanderers are the ultimate introverts of the universe, shunning the crowded stellar neighborhoods to roam the void alone. And their isolation isn't just a curiosity, it makes them some of the hardest objects in space to detect. Without the reflected light of a nearby star or the warmth of a busy system, they fade into the background like ghosts in the cosmic night. Take Y-0855, one of the coldest and closest known brown dwarfs. It's a mere 7.2 light-years away, practically our interstellar backyard. Yet it was only discovered in 2014 because its faint heat signature barely registers against the freezing depths of space. At -54 degrees Fahrenheit, it's colder than an Arctic winter, emitting just a whisper of infrared light. If it weren't for ultra-sensitive telescopes like the Wide Field Infrared Survey Explorer, we might never have noticed it at all. The challenges don't stop at detection. Studying these lonely giants is like trying to decipher a message written in invisible ink. Without the gravitational tugs or transits that reveal planets orbiting stars, astronomers have to rely on painstakingly slow methods, tracking their slight motions across the sky over years or analyzing the faintest chemical fingerprints in their light. Even then, surprises lurk. Some rogue brown dwarfs, like the mysteriously overcast SIMP J013656, defy atmospheric models entirely, hinting at weather patterns or compositions unlike anything seen in star-bound systems. Why so many loners? The leading theory suggests brown dwarfs are cosmic castaways ejected from their birthplace clusters by gravitational pinball in dense stellar nurseries. Others may have formed in place, collapsing from lonely gas pockets too meager to birth full stars. Whatever their origin, their solitude raises tantalizing questions. Could some harbor hidden, frozen worlds? Might their untethered journeys carry them through regions where life could hitch a ride? Every new discovery peels back another layer of their secrets, proving that sometimes the universe's most fascinating stories are the ones told in silence. In the cosmic taxonomy of stars and planets, brown dwarfs are the misfits that refuse to fit neatly into any box. Too massive to be planets, yet too small to sustain the hydrogen fusion that defines a true star. They exist in a frustrating gray zone that forces astronomers to constantly redraw the boundaries of classification. Imagine trying to categorize a creature that's half dolphin, half eagle. Science would stammer. And that's precisely what happens every time a new brown dwarf discovery appends our definitions. The root of the confusion lies in their stunted nuclear ambitions. A true star, like our Sun, thrives by fusing hydrogen into helium in its core, a process that requires immense pressure and temperatures exceeding 10 million degrees. Brown dwarfs, however, are cosmic underachievers. They may briefly ignite deuterium or lithium fusion in their youth, but their cores simply can't sustain the relentless atomic fire that keeps stars shining. They're like cars that sputter to life but never leave the driveway, doomed to cool and fade over billions of years. Yet calling them failed stars doesn't quite capture their defiance. Some, like those in the L-dwarf class, exhibit atmospheric chemistry closer to gas giants, while others, like the T-dwarfs, behave more like rogue planets adrift between stars. This identity crisis became glaringly obvious in 2014 when the object WISE J085510 83071442 was discovered. With a temperature colder than Earth's North Pole and a mass just 7 times Jupiter's, it forced astronomers to ask, is this a brown dwarf or a super-sized planet? The debate raged because traditional classification hinges on formation. Planets coalesce from disks around stars, while brown dwarfs collapse from gas clouds like stars. But what if a lonely object like this formed like a star yet shares traits with Jupiter? The lines blur until they vanish entirely. Even their spectral classification, the L, T, and Y types astronomers use to sort them, feels like a temporary fix. Y-dwarfs, the coldest known, ooze methane and water vapor like Jupiter, while warmer L-dwarfs sport titanium oxide clouds reminiscent of red stars, yet none truly belong to either camp. It's as if the universe handed us a celestial jigsaw puzzle where half the pieces are shaped like stars and half like planets, but the picture they form is something entirely new. Perhaps the most telling sign of their ambiguity is how often astronomers rewrite the rules to accommodate them. The International Astronomical Union once defined the boundary between planets and brown dwarfs at 13 Jupiter masses, the point where deuterium fusion can occur. But nature, as always, mocks human labels. Some 13 Jupiter mass objects act like planets, while others, like the free-floating rogue CFBD SIR 21490403, exhibit magnetic behaviors downright stellar in intensity. What brown dwarfs reveal, ultimately, is that our categories are human inventions, neat boxes that the cosmos cheerfully ignores. They challenge us to think beyond binaries, proving that the universe thrives in the in-between. And as we discover more of these boundary pushers, one truth becomes clear. Sometimes the most enlightening discoveries aren't the ones that fit our frameworks, but the ones that shatter them entirely. If you think a day on Earth passes quickly, try living on a hyperactive brown dwarf where the entire world whips around in less time than it takes to watch a movie. Some of these cosmic speed demons rotate so fast they flatten like pancakes, their equator bulging outward while their poles squeeze inward from the sheer force of motion. Take the record holder 2-mass J03486022, a brown dwarf that completes a full rotation in just 1.08 hours. That's faster than Jupiter spins, faster than any known planet, and dangerously close to the speed where centrifugal force could rip it apart. So how do these cosmic tops get spinning so wildly? Unlike stars, which often slow down over billions of years due to magnetic braking, brown dwarfs seem to cling to their youthful vigor. Many are born from collapsing gas clouds that conserve angular momentum, revving up as they shrink like an ice skater pulling in their arms to spin faster. But the real mystery is why some accelerate to extremes while others barely turn at all. Observations reveal a bizarre spread. While most brown dwarfs rotate once every few hours to days, outliers like 2-mass J03486022 defy logic, spinning at nearly 80% of their breakup speed. The consequences of this velocity are dramatic. At such breakneck rates, gravity struggles to hold the dwarf together, distorting its shape into an oblate spheroid, more like a squashed beach ball than a perfect sphere. This deformation isn't just cosmetic, it warps the object's entire magnetic field, stretching it into a lopsided dynamo that crackles with activity. Some of the most intense radio emissions from brown dwarfs come from these speedy spinners, where twisted magnetic lines snap and reconnect like cosmic rubber bands, unleashing plasma jets and auroras visible across light years. Yet the biggest puzzle lies in their stubborn refusal to slow down. Stars like our Sun shed rotation speed by flinging charged particles into space, tied to their magnetic fields like anchors. Brown dwarfs, though, seem to hit a wall where this braking effect weakens, possibly due to their shallower atmospheric layers or tangled magnetic geometries. The result, a population of eternal adolescents, spinning with reckless abandon long after their stellar siblings have settled into sedate middle age. The extremes don't stop there. Some theorists suggest these rapid rotators might harbor hidden jet streams or even supersonic winds in their upper atmospheres, where the difference in rotational speed between the equator and poles could spawn perpetual storms. Others speculate that their interiors might be stratified into rotating shells, like nested gyroscopes slipping against one another. One thing's certain, when a brown dwarf decides to spin, it doesn't do so quietly. It screams across the cosmos, leaving astronomers scrambling to decode the physics of a world where gravity and momentum wage an endless tug of war. Brown dwarfs aren't always the cosmic loners we imagine. Some come in pairs, locked in gravitational dances so tight they could fit inside our solar system's asteroid belt. These binary systems are like celestial mirror balls, spinning and swaying in ways that defy everything we thought we knew about how such objects behave. Take the system Lumen 16, just 6.5 light-years away, where two brown dwarfs whirl around each other every 27 years at a distance closer than Saturn is to the Sun. Their proximity creates a gravitational tug of war, distorting their atmospheres and sparking storms that ripple across both worlds simultaneously. What makes these duos so perplexing? For starters, they shouldn't exist according to early theories. Brown dwarfs form from collapsing gas clouds, a process that typically tears fragile pairs apart. Yet here they are, dozens of documented binaries, some so close their outer atmospheres nearly touch. The system 2-mass J1101-7732 is even more extreme. Its two dwarfs orbit each other in less than 5 years, separated by a gap narrower than Jupiter's distance from its largest moons. At that range, their magnetic fields must tangle like spaghetti, generating auroras that stretch between them like cosmic bridges. The real surprises come when these pairs interact. Infrared observations reveal that some binary brown dwarfs share heat unevenly, with one dwarf glowing significantly hotter than its twin despite similar ages and masses. One leading explanation points to tidal heating, the same force that keeps Jupiter's moon eovolcanic but cranked up to 11. As the dwarfs stretch and compress each other's interiors, friction builds, cooking one object from the inside out. It's as if they're locked in a perpetual wrestling match, trading energy back and forth in a competition with no clear winner. Then there's the mystery of mismatched pairs. Normally, binary stars or planets tend to have similar compositions, but brown dwarf duos break the mold. The system HD 130948 BC, for example, pairs a methane-rich T-dwarf with a hotter L-dwarf shrouded in silicate clouds. How such fundamentally different objects ended up gravitationally bound is anyone's guess. Did they capture each other late in life, or did they form together under conditions so bizarre they produced atmospheric chemistries worlds apart? The most tantalizing clue these systems offer lies in their orbits. Unlike star binaries, which often follow neat elliptical paths, brown dwarf pairs trace erratic, tilted trajectories. Some even loop around each other backward compared to their rotation, a sign of turbulent pasts, possibly involving close encounters with other stars that knocked them off kilter. Each oddball orbit is a fossil record of chaos, hinting at a youth spent in crowded stellar nurseries where gravitational shoves were as common as handshakes. Studying these pairs isn't just about cataloging cosmic quirks, it's a window into the physics of all failed stars. Their interactions expose hidden layers of magnetic activity, atmospheric mixing, and even the faint whispers of weather patterns echoing between them. And with every new binary discovered, the message grows clearer. Brown dwarfs don't play by solo rules. Whether they're trading heat, tangling magnetic fields, or defying compositional norms, these cosmic duos prove that isolation is just one chapter in their story, and often not even the most interesting one. Some brown dwarfs are cosmic escape artists, shedding their atmospheres so slowly you'd barely notice, until one day they're almost bare. Unlike stars, which cling to their outer layers for billions of years, or planets like Earth, shielded by gravity and magnetic fields, these dwarfs seem to leak their skies into space like punctured balloons. The evidence first surfaced in spectral data, where certain chemical signatures appeared fainter than expected, as if key ingredients were being siphoned away. Then came the smoking gun, Hubble observations of a brown dwarf called Wysia J 120,037, 79,784,508. 3. Its helium-rich atmosphere streaming behind it like a ghostly tail. So what's stripping these dwarfs bare? Stellar winds might play a role for those orbiting too close to larger stars, but the real culprits are often internal. Some brown dwarfs generate intense magnetic fields that funnel charged particles outward, creating a steady atmospheric bleed. Others, especially the hottest L-dwarfs, suffer from their own turbulent weather, superheated winds roaring at thousands of miles per hour, punching through gravity's grip. Imagine a hurricane so powerful it flings chunks of the sky into space. Now scale that up to a planet-sized storm with no solid surface to slow it down. The weirdest cases aren't gradual leaks but sudden collapses. Take the enigmatic brown dwarf known as 2-mass J 13,243,553 plus 6,358,281. Over a span of just 5 years, its methane absorption lines, a telltale sign of an intact atmosphere, dimmed by nearly 40%. One theory suggests it experienced a runaway cooling event, where sinking temperatures caused atmospheric gases to condense into rain and vanish beneath deeper layers. Picture a fog bank dissolving not into mist but into an abyss. Yet the most baffling vanishings involve dwarfs losing specific elements while retaining others. One object might hemorrhage hydrogen but cling stubbornly to its sodium, while another dumps carbon monoxide but keeps its iron clouds. This selective stripping hints at layers of atmosphere peeling apart like an onion, each with its own escape velocity and chemical quirks. Some astronomers compare it to distilling whiskey, heat and motion, separating lighter compounds from heavier ones, leaving behind a brew no one expected. The implications are staggering. If brown dwarfs can lose their atmospheres entirely, some of the rogue planets we've detected floating between stars might actually be stripped-down dwarfs in disguise. Worse, their evaporation rates don't always match predictions, suggesting our models of atmospheric physics are missing something fundamental. Whether it's magnetic surprises, hidden energy sources, or exotic chemistry, these vanishing acts prove that in the cosmos, even the air you breathe isn't guaranteed to stick around. If there's one molecule that shouldn't survive the heat of a star, it's methane. This fragile hydrocarbon breaks apart at temperatures above 1,000 degrees Fahrenheit, yet bizarrely, it thrives in the atmospheres of some brown dwarfs. These objects straddle the line between planet and star so awkwardly that they host chemistry textbooks should have told us was impossible. Take the T-type dwarfs, a class of brown dwarfs so cool their skies swirl with methane clouds, giving them a distinctly Jupiter-like vibe. It's as if someone took a gas giant and cranked up the mass until it nearly became a star, but forgot to tell the atmosphere it was supposed to act like one. The puzzle deepens when you realize methane isn't just present, it's abundant. In cooler brown dwarfs like Gliese 57d, methane dominates the infrared spectrum, absorbing light so aggressively it creates a telltale fingerprint astronomers can spot across interstellar distances. But here's the twist: methane shouldn't form so easily in these environments. At the temperatures and pressures found in many brown dwarfs, carbon and hydrogen atoms should prefer bonding into carbon monoxide or complex hydrocarbons, not settling into simple methane. Yet somehow, these objects defy equilibrium chemistry, crafting methane-rich atmospheres that behave more like Saturn's moon Titan than a failed star. One theory suggests violent convective currents are to blame. Unlike true stars, where heat rises smoothly from the core, brown dwarfs churn like overzealous lava lamps, dredging up deep layers where carbon and hydrogen have mellowed into methane and flinging them to the surface before they can break apart. Picture a cosmic blender set to turbo, constantly recycling the atmosphere's ingredients into unexpected combinations. Other researchers point to photochemistry, high-altitude reactions where ultraviolet light from distant stars reshuffles atmospheric molecules like a deck of cards, favoring methane's formation against all odds. The real stunners are the methane deserts, brown dwarfs where methane should flourish but is conspicuously absent. The object known as 2-mass J09392448, for example, has temperatures perfect for methane production, yet scans reveal barely a trace. Astronomers suspect these methane droughts might stem from silicate clouds high in the atmosphere, acting like a chemical sponge that soaks up carbon before it can bond with hydrogen. Or perhaps ferocious winds strip methane away faster than it can form, leaving behind an atmospheric wasteland where the rules of chemistry seem rewritten. What makes these methane mysteries so pivotal is what they reveal about the blurry boundary between planets and stars. Brown dwarfs with methane-rich skies challenge our assumptions about how celestial objects evolve, proving that temperature alone doesn't dictate atmospheric chemistry. They're cosmic alchemists turning stellar ingredients into planetary conditions, and in doing so, forcing us to rethink everything we thought we knew about the chemistry of the cosmos. Young brown dwarfs have a habit of showing off, launching jets of material so powerful they rival those of full-fledged stars. These aren't gentle wisps of gas but violent, focused beams shooting light years into space, carving through cosmic dust like celestial blowtorches. The first time astronomers spotted one, they nearly dismissed it as an instrument error. After all, objects this small weren't supposed to produce such stellar-scale fireworks. Yet there it was, a brown dwarf barely 20 times Jupiter's mass, spewing a jet stretching 3 times the length of our solar system. How does something so compact punch above its weight? The secret lies in the chaotic birth of these objects. When a brown dwarf forms, it doesn't just quietly condense from a gas cloud, it's born kicking and screaming. As gravity collapses the surrounding material into a dense core, leftover gas spirals inward at breakneck speeds, forming a spinning disk. But not all that material makes it onto the brown dwarf. Some gets funneled along magnetic field lines, accelerating to nearly 100 kilometers per second before shooting out from the poles in twin jets. Picture a garden hose with the nozzle cranked to maximum, except instead of water, it's blasting superheated plasma across light years, the weirdest part. These jets behave nothing like their stellar counterparts. While massive stars produce relatively steady streams, brown dwarf jets come in erratic bursts, flickering on and off like a cosmic strobe light. The young brown dwarf Mayer at 120317, for example, fires off sporadic bullets of gas every few months, each one packing enough energy to outshine the dwarf itself temporarily. Astronomers suspect this stop-start pattern stems from clumpy accretion, the brown dwarf gulping down chunks of disk material unevenly, triggering violent releases of pent-up energy. Then there's the composition mystery. Stellar jets are mostly hydrogen and helium, but brown dwarf jets often carry heavier elements like iron and silicon debris from the dusty disk they're devouring. In some cases, these jets even contain complex organic molecules, the kind we associate with planet-forming regions. It's as if the dwarf is belching out ingredients for future worlds while still struggling to become a star itself. Perhaps the most baffling discovery came when radio telescopes caught a jet-emitting polarized light, a sign of magnetic fields strong enough to twist the very fabric of the outflow. This suggests brown dwarfs don't just borrow stellar physics, they warp them into something new. Whether it's their patchy ejection patterns, unexpected chemistry, or magnetic gymnastics, these gravity-defying jets prove one thing. When it comes to cosmic rule breaking, brown dwarfs don't just bend the rules. They rewrite them. Spotting a brown dwarf is like trying to find a black light bulb in a dark room. It's there, but nearly everything we use to see fails to catch it. These cosmic phantoms emit almost no visible light, fading into the background of space so effectively that even some of our most powerful optical telescopes overlook them entirely. While stars announce themselves with brilliant flares and planets often reflect sunlight, brown dwarfs linger in the shadows, radiating only faint whispers of heat. It's not that they're rare. Astronomers estimate our galaxy could harbor billions, but their stealth makes them some of the most elusive objects in the universe. The problem starts with temperature. A typical brown dwarf cools rapidly after formation, plunging to mere hundreds of degrees Fahrenheit, sometimes even colder than a winter night on Earth. At these temperatures, they don't glow with the fiery light of stars but emit weakly in the infrared spectrum, like dying embers in a cosmic campfire. Early sky surveys tuned to visible light swept right past them. Even now, the coldest known y-dwarfs, some chilling below room temperature, are detectable only because space itself is colder, creating just enough contrast for specialized instruments to pick up their thermal signatures. Enter the infrared revolution. Telescopes like NASA Spitzer and the Wide Field Infrared Survey Explorer WISE changed the game by seeing the universe in heat vision. WISE alone discovered over 100 previously hidden brown dwarfs, including some shockingly close to our solar system. But the tech isn't simple. Infrared detectors must be cooled to near absolute zero to avoid drowning out the faint signals from these objects with their own heat. Even then, distinguishing a brown dwarf from distant galaxies or interstellar dust requires analyzing subtle spectral fingerprints, like identifying a person by their shadow in a crowded room. The challenges don't end at detection. Brown dwarfs often masquerade as other cosmic phenomena. Their spectra can mimic distant stars or even exoplanets, leading to cases of mistaken identity. One notorious example is the object known as WISE 1828+2650, initially flagged as a possible rogue planet until its temperature, barely warmer than a household oven, confirmed it as one of the coldest brown dwarfs on record. Without the right tools, these objects slip through the cracks, their true nature hidden behind cosmic camouflage. Why does this invisibility matter? Because every undiscovered brown dwarf represents a gap in our understanding of stellar evolution, planet formation, and even the galaxy's hidden structure. Some could be floating just beyond the solar system's edge, influencing the orbits of distant comets. Others might hold clues to how planetary systems, including our own, were born. Thanks to next-generation telescopes like the James Webb Space Telescope, we're finally pulling back the curtain on these shadowy giants. But for every one we find, countless others likely remain, waiting in the dark for their moment to step into the light. Storm systems on brown dwarfs make Jupiter's legendary tempests look like gentle breezes. While the Great Red Spot has raged for centuries with winds topping 400 miles per hour, brown dwarfs unleash atmospheric chaos on an entirely different scale. Take the case of 2 mass J 10,475,385 plus 2,124,234, a brown dwarf where storms whip across the sky at over 1,400 miles per hour, fast enough to cross the continental United States in under 2 hours. These aren't just storms, they're hypercanes swirling with molten minerals and charged particles that turn the upper atmosphere into a cosmic particle accelerator. What fuels these monstrous weather systems? Unlike Jupiter, where storms are driven by solar heating and internal energy, brown dwarf tempests arise from a perfect storm of conditions. With no solid surface to disrupt airflow, winds spiral unimpeded around the globe, gaining speed like a runaway turbine. Meanwhile, extreme temperature gradients, some dwarfs have poles hundreds of degrees cooler than their equators, create pressure differentials that slam air masses together with unimaginable force. The result, storms that don't just last for years, but for centuries, with lightning strikes so powerful they could vaporize entire cities in a single flash. The lightning itself is something out of a science fiction nightmare. On Jupiter, electrical discharges occur between ammonia-rich clouds and water layers beneath. But on hotter brown dwarfs, the clouds are made of vaporized metals like iron and silicates, creating lightning that crackles with molten conductivity. Observers have detected radio bursts from dwarfs like Lumen 16b that suggest lightning storms spanning continents. Their discharges 1,000,000 times more energetic than Earth's strongest superbolts. Some theorists even speculate these electrical monsters might trigger exotic atmospheric chemistry, forging complex molecules in their searing aftermath. The most mind-bending feature, brown dwarf storms don't follow predictable patterns. Jupiter's Great Red Spot is remarkably stable, but brown dwarf vortices split, merge, and vanish like phantoms. Infrared time lapses of the dwarf WISE 2209 plus 2711 revealed a dozen megastorms forming and dissipating within a single Earth year, some leaving behind storm scars, darkened atmospheric belts where clouds were shredded by the violence. It's as if these failed stars have atmospheric memories, their skies permanently altered by weather gone rogue, yet the true oddity lies in their silence. No spacecraft will ever plunge into these maelstroms to measure them directly, so astronomers must decode their secrets from light years away. Each flicker of infrared brightness, each shift in spectral lines, tells a story of a world where the weather doesn't just change with the seasons, it rewrites the rules of meteorology itself. In the cosmic game of aging, brown dwarfs are the ultimate cheaters. Some look suspiciously youthful compared to their stellar neighbors, flouting every rule we have about how these objects should cool and dim over time. Astronomers first noticed this anomaly when studying clusters where all stars formed together, like siblings from the same stellar nursery. While most brown dwarfs in these groups behaved predictably, cooling steadily as expected, a rebellious few glowed with the vigor of objects half their age, as if they discovered some cosmic fountain of youth. Take the case of the Pleiades cluster, a star group famously young at just around 100 million years old. Nestled among its bright blue stars, researchers found brown dwarfs that should have been cooling rapidly, yet some burned stubbornly bright, their infrared signatures matching objects theoretically 10 times younger. It's like finding a gray-haired toddler in a preschool photo. The mismatch defies logic. One standout, dubbed Tade 1, emitted so much excess heat that initial estimates pegged it as a newborn until its membership in the ancient cluster betrayed its true age. What's keeping these dwarfs artificially spry? One radical theory suggests internal thermal rebellions, episodes where trapped heat from their violent formation suddenly resurfaces, like a sealed thermos shaking and belching steam years after being filled. Others point to gravitational kneading from undiscovered planets or binary companions, stirring the dwarf's interior like a spoon swirling in coffee, redistributing warmth that should have escaped eons ago. Then there's the wild card, magnetic fields so intense they act as insulation, slowing the escape of thermal energy like a stellar GRADE Chinese letter. The most baffling cases show no obvious cause at all. The brown dwarf WISEP J190648, 47 plus 401,106, 8, isolated and companionless, cools at a rate 20% slower than models predict. Its heat lingers like a dying ember that refuses to fade, whispering of processes we haven't yet imagined. Some astronomers wonder if these objects might harbor exotic phases of matter in their cores, dense, degenerate states where heat propagates weirdly, or even quantum phenomena that alter energy flow at macroscopic scales. What makes these age-defying dwarfs more than just cosmic curiosities is what they reveal about the limits of our physics. Stellar aging models, honed over decades, assume a tidy universe where objects lose heat predictably. But nature, as always, scoffs at human assumptions. Every anomalously youthful brown dwarf is a clue, a signpost pointing toward gaps in our understanding of thermodynamics, fluid dynamics, or even the fundamental behavior of matter under extreme conditions. Perhaps the most humbling lesson is this: in a cosmos where even failed stars can outsmart our best theories, the line between ignorance and discovery is often just a matter of looking closer. And with each new maverick brown dwarf that refuses to fade gracefully into old age, the universe reminds us that its greatest mysteries aren't always written in the stars, but sometimes in the shadows between them. If stars had permanent records, brown dwarfs would be the master forgers, shifting their spectral identities so dramatically over time that astronomers sometimes struggle to recognize the same object across decades of observations. Unlike stars, which spend billions of years burning steadily as the same spectral type, brown dwarfs are cosmic shape-shifters, cooling and transforming so radically that their entire classification can change within a human lifetime. It's as if the universe handed them a disguise kit, letting them masquerade first as one celestial archetype, then another, all while hiding their true nature in plain sight. This spectral sleight of hand begins with their failed stardom. A young brown dwarf might start its life mimicking a dim M-type star, glowing a dull red with temperatures around 2000 degrees Fahrenheit. But without nuclear fusion to sustain it, the dwarf cools rapidly. Within a few 100 million years, it transitions to an L-type, its atmosphere now dotted with thick clouds of molten iron and silicates. Give it another billion years and it sheds even that heat, morphing into a T-type dwarf where methane runs rampant and the sky takes on a deep, Jupiter-like hue. The coldest of the bunch eventually reach the Y-type category, so frigid that water vapor freezes into icy hazes, and their infrared glow becomes barely distinguishable from the background chill of space. The real magic happens in the details of these transformations. Take the brown dwarf known as 2-mass J0415195409350066, observed first in the 1990s as a standard L dwarf. By 2015, follow-up spectroscopy revealed its atmosphere had cooled enough for methane to dominate, silently crossing the threshold into the T-type class. What seems like a quiet transition is actually a total atmospheric revolution, chemical reactions slowing, cloud decks collapsing, and magnetic fields weakening as the dwarf settles into its new identity. But the plot thickens when these changes don't follow the script. Some brown dwarfs, like the enigmatic WISE J085510, 8307-1442, 5, cool so slowly they stall for eons in one spectral class, defying predictions. Others leapfrog entire categories, their cooling accelerated by unknown factors, perhaps interactions with interstellar material or latent heat from gravitational contraction. Then there are the spectral imposters, like the case of SDSS J141624, 08 plus 134,826, 7, which oscillates between L and T characteristics depending on which chemical signatures astronomers prioritize. Is it a methane-rich T-dwarf with lingering L-type traits, or an L-dwarf with freakishly early methane production? Even the classifications argue among themselves. This chameleon act isn't just academic, it's rewriting how we map the cosmos. Surveys that rely on spectral typing to estimate distances and ages must now account for brown dwarfs that have changed teams mid-game. A faint T-dwarf in one catalog might be the same object as a brighter L-dwarf in another, separated not by space but by time. And with next-generation telescopes poised to discover thousands more of these spectral fugitives, one thing's clear. In the universe's grand game of celestial disguise, brown dwarfs aren't just players, they're the undisputed champions. Among the cosmic oddballs, few things disrupt theories like a brown dwarf crashing a star's planetary party. Imagine a solar system where, instead of neat concentric orbits, a massive, smoldering dwarf looms among the planets, squatting in the zone where gas giants should reign, yet dwarfing them in size and chaos. These aren't hypothetical. Systems like HD 33632 host a brown dwarf orbiting so close to its star that it defies conventional formation models. At just 20 times Jupiter's mass, this interloper sits where a planet ought to be, its sheer gravitational presence warping the disk of debris that might have birthed smaller worlds. But the real head-scratchers are the circumbinary brown dwarfs, those that orbit two stars at once. Take the system BD-225861, where a brown dwarf dances around a pair of sun-like stars like a cosmic third wheel. According to planet formation theories, the gravitational turbulence from binary stars should shred any nearby protoplanetary disks, preventing massive objects from coalescing. Yet there it is, a 70 Jupiter-mass dwarf stubbornly existing where it shouldn't. One theory suggests it formed farther out and migrated inward, elbowing past the star's gravitational defenses like a boulder rolling downhill. Others argue it might be a captured rogue, snatched from interstellar space, but that raises new questions about how such a delicate gravitational heist could occur without ejecting the star's existing planets. Even wilder are the hierarchies where brown dwarfs orbit other brown dwarfs, creating a Russian nesting doll of failed stars. The System 2 mass J0 10335 635,515,561 pairs two nearly identical dwarfs separated by less than 3 times the Earth-Sun distance. They whirl around each other so closely that their magnetic fields may tangle, sparking auroras visible light years away. These binaries shouldn't exist under classic formation scenarios where collapsing gas clouds typically fragment into single objects or wide-spaced pairs. Their tight orbits hint at chaotic beginnings, perhaps a triplicate system where one dwarf was violently ejected, leaving the remaining two locked in a gravitational embrace. The implications ripple across astronomy. If brown dwarfs can form or survive in orbits reserved for planets, our definitions of planet and star grow even blurrier. Worse, their presence may explain mysterious gaps in protoplanetary disks or the skewed orbits of exoplanets. Every misfit companion we discover is a wrench in the gears of formation theories prove that the universe cares less about our categories than it does about chaos, opportunity, and the occasional celestial prank. Brown dwarfs may lack the roaring stellar winds that define their full-fledged stellar cousins, but don't mistake their silence for weakness. These cosmic underdogs wield magnetic fields so intense they could make a neutron star blush. While stars like our Sun bombard space with a constant barrage of charged particles, solar winds that sculpt planetary atmospheres and ignite auroras, brown dwarfs keep their fury locked beneath a deceptively calm exterior. Yet when their magnetic fields snap, the results are anything but quiet. The absence of stellar winds comes down to their failed stardom. True stars generate winds through their churning outer layers and searing coronae, where magnetic loops heat plasma to millions of degrees until it escapes gravity's grip. Brown dwarfs, though, are too cool to sustain those conditions. Without a blazing corona to energize particles, their atmospheres cling tightly, like a steamless kettle sitting cold on a stovetop. But here's the twist. Their magnetic fields often rival those of low-mass stars, some reaching thousands of times stronger than Jupiter's. These fields don't dissipate gently, they store energy like coiled springs, waiting to unleash chaos. Take the case of the brown dwarf LSRJ 1835 plus 3259, where astronomers detected a flare so powerful it briefly outshone the dwarf's entire infrared output. The culprit, a magnetic reconnection event, a violent snap of twisted field lines that accelerates electrons to near light speed, sparking auroras visible across radio frequencies. Unlike solar flares, which release energy outward via winds, brown dwarf flares erupt inward, their plasma arcs trapped by gravity and funneled back into the atmosphere. It's like lightning striking downward and then ricocheting off an invisible ceiling, superheating the air in a feedback loop of destruction. The real danger lies in their unpredictability. Stars often telegraph their outbursts through sunspot cycles or wind patterns, but brown dwarfs strike without warning. Radio observations of the dwarf SIMP J0 1365663 plus 093347 revealed pulses of polarized emission, a sign of electrons spiraling along magnetic field lines so twisted they resemble tangled spaghetti. When these fields finally unwind, they don't just spark auroras, they can strip atmospheres, ionize nearby gas clouds, or even fry hypothetical orbiting planets with radiation spikes. What makes these hidden tempests so eerie is their invisibility. Without the telltale solar winds to announce their presence, a brown dwarf might appear benign until its magnetic snare triggers. Some theorists speculate these silent surges could explain why certain exoplanets orbiting dwarfs have mysteriously lost their atmospheres. The mechanism wouldn't be gradual erosion but violent, episodic bombardments, like an invisible cosmic predator striking from the shadows. Yet for all their destructive potential, these magnetic tantrums may also forge opportunity. The same processes that threaten planets could seed molecules in their atmospheres, sparking probiotic chemistry in unexpected places. It's a paradox that defines brown dwarfs, too weak to be stars, too wild to be planets, and forever dancing on the edge of cosmic extremes. Their silence isn't surrender, it's the calm before storms we're only beginning to comprehend. Buried deep inside some brown dwarfs, a glittering spectacle might be unfolding, one where the very skies rain diamonds. This isn't science fiction, it's a serious hypothesis born from the bizarre physics of these cosmic misfits. Under pressures millions of times greater than Earth's atmosphere and temperatures soaring to thousands of degrees, carbon atoms could be crushed into crystalline diamonds, falling like precious hail through layers of scalding gas. The idea first gained traction when astronomers noticed puzzling gaps in the infrared spectra of certain brown dwarfs' absorption lines that hinted at carbon being yanked out of circulation. possibly sequestered into solid form. The recipe for this cosmic gem factory starts with methane, a molecule common in cooler brown dwarfs. As temperatures and pressures rise toward the dwarf's interior, methane breaks apart, releasing carbon atoms. Normally, these would bond with oxygen or other elements, but in the crushing depths of a brown dwarf's atmosphere, something stranger happens. The carbon gets squeezed until its atomic structure collapses into the tightly packed lattice of diamond. Picture a carbon-rich fog hardening into microscopic gems midair, then cascading downward until the heat below vaporizes them back into gas, completing a glittering cycle of creation and destruction. The wildest twist, this process might not be steady. Some models suggest diamond rain could arrive in violent waves, triggered by convective currents or shock waves rippling through the dwarf's interior. Imagine a storm where diamond raindrops the size of grains of sand, or even boulders pelt through neon-rich clouds, only to dissolve long before reaching any surface. The closest analog in our solar system is Neptune, where lab experiments hint at diamond formation under similar extremes. But brown dwarfs take it to another level, with pressures so intense that diamonds might even assemble into exotic, hot ice phases or melt into electrically conductive oceans. A far cry from the gemstones in a jewelry store. Yet the diamond rain hypothesis isn't without skeptics. Alternative explanations for the missing carbon include chemical reactions we haven't discovered or carbon locked into soot-like particles too small to detect. Others argue that diamonds, if they exist, might never fall at all, instead suspended in a turbulent atmosphere like glitter in a snow globe. What makes the idea so tantalizing is what it reveals about the hidden machinations of these objects. If proven, diamond rain would expose brown dwarfs as alchemists, transmuting mundane elements into treasures under conditions we can barely replicate on Earth. It's a reminder that the universe's most dazzling wonders often lurk where we least expect them, not in the blazing hearts of stars, but in the stormy depths of the cosmos's greatest underachievers. Auroras on Earth paint the sky with luminous ribbons of green and purple, sparked by charged particles from the solar wind colliding with our atmosphere. But brown dwarfs, those cosmic misfits, neither star nor planet, create their own light shows without any stellar help at all. These ghostly auroras glow in radio waves and infrared, sometimes outshining the dwarf's own thermal radiation, and their existence defies everything we thought we knew about how celestial light displays form. Without a star's relentless solar wind to energize their atmospheres, how do these solitary objects conjure such brilliance? The answer lies in their turbulent interiors. Brown dwarfs generate magnetic fields thousands of times stronger than Jupiter's, twisting and snapping like live wires in a storm. When these fields reconnect, they catapult electrons toward the dwarf's poles at nearly light speed, where they slam into atmospheric gases, hydrogen, helium, even ionized sodium, igniting auroras visible across light years. The process mirrors Earth's northern lights, but scaled up to a staggering degree. Imagine an aurora so vast it could wrap around Jupiter, fueled entirely by the dwarf's internal chaos rather than an external star. Even stranger, some of these auroras might owe their existence to hidden planets. Just as Jupiter's moons Io and Europa electrify its magnetic environment with their volcanic plumes and icy geysers, a large orbiting world could inject fresh particles into a brown dwarf's magnetosphere. The object known as LSRJ 1835 plus 3259, for example, pumps out radio auroras with eerie regularity, pulses so precise they hint at an unseen companion stirring the pot. If confirmed, this would mark the first evidence of planet-driven auroras outside our solar system, a tantalizing glimpse of how cosmic neighbors can light up the darkness together. The most baffling cases, though, show no planetary accomplice at all. Take the brown dwarf SIMP J0136563 plus 0933473, whose auroras flicker unpredictably, their radio waves spiraling through space like distorted sirens. Here, the energy seems to come from deep within, perhaps from convective currents dredging up ions from the dwarf's core, or from pockets of plasma trapped in magnetic loops that suddenly rupture. It's as if the dwarf is playing cosmic pinball with its own atmosphere, bouncing particles around until they erupt in dazzling displays. What makes these auroras so unsettling is their sheer independence. Unlike planetary light shows, which wax and wane with their star's mood, brown dwarf auroras answer to no one. They flicker to life in the void, untethered from any stellar influence, proving once again that these objects don't just blur the line between star and planet. They rewrite the rules of cosmic physics along the way. Brown dwarfs aren't just celestial oddballs, they're cosmic historians, preserving snapshots of the universe's youth in their dimly glowing atmospheres. Unlike stars, which churn and recycle their interiors over billions of years, these failed stars cool so gradually that their chemical makeup remains eerily unchanged since their formation. It's as if they've been sealed in galactic amber, trapping primordial gases and ancient isotopes that would have vanished in hotter, more active stellar environments. The brown dwarf WISE 1852 plus 3538, for instance, carries an atmosphere nearly untouched by time. Its hydrogen laced with deuterium, a heavy isotope abundant in the early universe but now incredibly rare. This time capsule quality makes them invaluable to astronomers. Picture a cosmic archaeologist sifting through layers of sediment, except instead of pottery shards, they're analyzing the infrared spectra of a brown dwarf's methane bands, uncovering traces of elements forged in the galaxy's first stellar generations. Some ultra-cool y-dwarfs, like those in the WISE survey, even exhibit anomalously high metallicity, hinting at a birth environment polluted by the ashes of long-dead supernova. By studying these ancient fingerprints, researchers can reconstruct the chemical evolution of the Milky Way, tracing how heavier elements spread through the cosmos like ink in water. The real breakthrough came when astronomers realized certain brown dwarfs might be first-generation relics objects formed from nearly pure hydrogen and helium, much like the universe's earliest stars. While no pristine examples have been confirmed yet, candidates like Euler's J001535 72 plus 01567.9 showed tantalizingly low metal content, suggesting they coalesced from gas barely touched by stellar nucleosynthesis. If verified, these dwarfs could offer a direct window into the era before planets or even carbon-based chemistry existed. But their archival powers don't stop at chemistry. Brown dwarfs also preserve dynamical clues about the Milky Way's violent past. Isolated halo dwarfs orbiting far from the galactic disk, such as SDSS J010448, 46 plus 153525.8, move on eccentric paths that mirror the trajectories of ancient star clusters ripped apart by tidal forces. Their lonely journeys trace gravitational scars left by mergers with dwarf galaxies billions of years ago, events that shaped the Milky Way but left few other witnesses. Perhaps most remarkably, these cosmic archivists challenge our assumptions about galactic timelines. Cooling models once suggested the coldest brown dwarfs must be ancient, but new discoveries reveal outliers like WISE 0811-1415, which appears far too chilly for its estimated age. This discrepancy hints at gaps in our understanding of early star formation, rates, or even the possibility of exotic cooling mechanisms lost to time. Every anomaly is a breadcrumb leading back to the universe's untold stories, and in the atmospheres of these failed stars, the past isn't just remembered. It's still glowing. Some brown dwarfs don't just drift lazily through the galaxy, they barrel through the void like cosmic outcasts flung from their birthplaces with enough speed to escape stellar clutches forever. These runaway objects are the interstellar equivalent of a slingshot projectile, ejected from the dense stellar nurseries where they formed with velocities that can exceed 500,000 miles per hour. The first hint of their existence came when astronomers noticed oddballs like SIMP J0, 1365663 plus 093347 hurtling through space alone, their paths tracing backward to violent star-forming regions where gravitational chaos reigns. The ejection process is anything but gentle. Picture a crowded stellar nursery where young stars and brown dwarfs jostle for position in a gravitational free-for-all. When multiple massive stars pass too close, their combined gravity can fling smaller objects outward like a cosmic slingshot, a phenomenon known as dynamical ejection. The brown dwarf 2-mass J0348 Aero77 2-6,022,270, for instance, moves at over 300,000 miles per hour, its trajectory suggesting it was punted clear of the Theta Orionis cluster by a close encounter with heavier siblings. Some runaways may even be the survivors of failed triple systems, where one dwarf was violently ejected while the other two merged or tightened their orbit, releasing enough energy to send the third flying. But speed isn't the only clue to their traumatic pasts. Runaway brown dwarfs often spin unusually fast, their rotation rates revved up by the same gravitational kicks that sent them careening. The object CFB DJ005910 90011401 for example, rotates once every 2 hours, likely a souvenir from the moment it was sent spinning into the abyss. Others, like the hypervelocity dwarf 2-mass J 1119-1137, show atmospheric scars, chemical imbalances or storm patterns frozen in time, as if their atmospheres were half-stripped during the violent exit. The most extreme cases blur the line between ejection and explosion. The brown dwarf Wysia J 114724 10-204,021 races away from the TW Hydra Association with such velocity that astronomers suspect it wasn't just flung, it was launched by a supernova's shockwave. If true, it carries the fingerprint of a stellar explosion powerful enough to turn a failed star into an interstellar cannonball. Yet for all their drama, these runaways are more than just celestial curiosities. Their trajectories serve as cosmic breadcrumbs, leading back to the gravitational battles that shaped their origins. And with every new hypervelocity dwarf discovered, astronomers gain fresh insights into the turbulent youth of star clusters, where the difference between staying and fleeing comes down to a single, chaotic moment in time. When you picture a dying star, you probably imagine a supernova, a cataclysmic explosion that rips through space in a blaze of glory. But brown dwarfs, they bow out with a whimper, not a bang. These cosmic underdogs lack the mass to die dramatically, quietly cooling into oblivion over trillions of years without so much as a farewell firework. Yet their subdued exits hold mysteries that challenge our understanding of stellar evolution. Take the myth of brown dwarf explosions, a persistent idea fueled by their star-like origins. While true stars perish in spectacular supernovas or collapse into dense neutron stars, brown dwarfs never muster the core pressures needed for such theatrics. Their nuclear engines sputter out early, leaving them to fade like embers in a campfire. But here's the twist: their deaths aren't as simple as just cooling down. Simulations suggest some may undergo miniature carbon flashes, late in life brief, feeble bursts of fusion reignited as their cores compress, burning residual carbon like a car backfiring on its last drop of fuel. These flickers are a far cry from supernovas, but they hint at a death throes we've yet to witness directly. The real enigma lies in their corpses. A true star's corpse, a white dwarf or neutron star, leaves a dense, glowing remnant. Brown dwarfs, though, could become something stranger, degenerate spheres of hydrogen and helium, so cold and ancient they're virtually invisible. Some theorists speculate these husks might crystallize over eons, their interiors freezing into exotic quantum states akin to giant cosmic ice cubes. Others argue they could collapse further, forming black dwarfs, hypothetical, pitch-dark relics so cold they emit no light at all. The catch: the universe isn't old enough for any brown dwarf to have reached this stage yet. We're left peering into a future nobody's seen. Even their final interactions with the cosmos defy expectations. Unlike stars, which seed galaxies with heavy elements when they explode, brown dwarfs hoard their primordial ingredients. Yet their gravitational whispers might still sculpt their surroundings. A slow-motion ballet of decay could nudge nearby objects over millennia, or their lingering heat might temporarily warm rogue planets passing by. The quietest deaths, it seems, can still ripple through eternity. So while brown dwarfs will never light up the sky with a supernova's grandeur, their farewells are anything but ordinary. They challenge us to rethink how objects fade, what remnants they leave behind, and whether the universe's most unremarkable deaths might hide the most remarkable secrets. Brown dwarfs may be cosmic loners, but don't mistake their solitude for insignificance. These shadowy giants could be the unseen puppeteers of the galaxy, silently tugging at the strings of star systems without ever revealing themselves. Think of them as celestial ghosts, their gravitational whispers nudging planets, bending comet paths, and even redirecting entire stellar neighborhoods over millennia. The evidence lies in the anomalies, the misaligned orbits of distant worlds, the rogue comets flung off course for no apparent reason. Some astronomers suspect brown dwarfs are the hidden architects behind these cosmic oddities, their quiet presence rewriting the stories of systems they never joined. Consider the case of HD 106906b, a gas giant exoplanet orbiting its star at a tilt so extreme it defies traditional formation models. A passing brown dwarf, unseen but inferred, might be the culprit, its gravity yanking the planet's orbit askew like a bully kicking a soccer ball mid-game. Simulations show a single close encounter with a brown dwarf could torque a planetary system's alignment by dozens of degrees, leaving no trace except the chaos in its wake. The dwarf wouldn't linger, it would vanish back into the dark, leaving astronomers to piece together the gravitational crime scene. Then there's the Oort cloud, that icy graveyard of comets at our solar system's edge. Some researchers propose that undiscovered brown dwarfs loners drifting between stars could periodically plow through this fragile shell, sending comets careening inward toward the sun. These icy trespassers might explain sudden spikes in comet activity throughout Earth's history, even mass extinctions tied to cosmic bombardment. The brown dwarfs responsible wouldn't announce their visits. They'd slip by unnoticed, their gravity the only signature of their passage. The most tantalizing possibility: brown dwarfs might be the missing link in some of astronomy's greatest puzzles. Take the hypothetical Planet 9 at our solar system's fringe. Could it actually be a rogue brown dwarf, its faint glow lost in the noise of the cosmos? Or consider the bizarre orbits of dwarf galaxies around the Milky Way, which some models suggest could be shaped by dark, substellar interlopers lurking in the galactic halo. What makes these unseen influencers so unnerving is their elusiveness. Unlike black holes, which warp spacetime dramatically, or stars, which blaze with obvious intent, brown dwarfs operate in the shadows. They're the cosmic equivalent of a rumor felt but not seen, their influence etched into the trajectories of other objects long after they've moved on. And as our telescopes grow sharper, we may finally catch these phantoms in the act, proving that sometimes the universe's most powerful players are the ones we never thought to look for. At the far end of the brown dwarf spectrum lurk the y-dwarfs, cosmic phantoms so cold and faint they blur into the frigid background of space itself. These twilight zone residents push the limits of what we consider a failed star, with surface temperatures dipping below 80 degrees Fahrenheit colder than a winter day on Earth. The first confirmed y-dwarf, WISE 0855-0714, stunned astronomers by registering a frosty negative 54 degrees, barely warmer than the cosmic microwave background radiation left over from the Big Bang. What makes these objects so eerie isn't just their temperature, it's how they rewrite the rules of visibility. Unlike stars or even warmer brown dwarfs, y-dwarfs emit almost no visible light, lurking in the infrared like thermal ghosts. Detecting them requires instruments chilled to near absolute zero, just to avoid drowning out their faint heat signatures with the telescope's own warmth. The discovery of WISE 1828+2650, a y-dwarf barely hotter than a household oven, revealed just how stealthy these objects can be. It was practically invisible until infrared eyes peeled back the cosmic darkness. Yet their chill hides surprising complexity. Some y-dwarfs sport ammonia clouds or water vapor hazes, their atmospheres resembling a cross between Jupiter and a freezer-burned comet. Others, like WISE 0350-5658, show spectral hints of methane snow-tiny particles crystallizing in skies where the sun never shines. The coldest specimens might even host exotic ammonia-based weather systems, with storms brewing in chemical soups no planet could replicate. The real puzzle is how these cosmic ice cubes form in the first place. Traditional brown dwarf cooling models struggle to explain why some y-dwarfs are colder than their ages should allow, as if they've discovered a secret refrigeration method. One theory suggests they're galactic strays, objects born in sparse regions with little material to heat their cores. Another posits they siphoned energy from unseen companions or drifted through cold gas clouds, bleeding heat faster than expected. Their kinship with rogue planets only deepens the mystery. At masses barely 5 times Jupiter's, the line between y-dwarf and gas giant evaporates entirely. The object WISE 1541-2250, for instance, has a temperature matching Jupiter's but with no star to call home. Is it a dwarf or a planet? The distinction matters less than the revelation. In the coldest corners of space, the universe crafts objects so strange they force us to rethink every label we've ever invented. Deep within the smoldering atmospheres of certain brown dwarfs, invisible forces churn with terrifying intensity, magnetic fields so powerful they could strip the electrons from atoms at 100 paces. These magnetic monsters don't just nudge particles around, they twist space into knots, unleashing energy tantrums that outshine their host dwarfs entirely. Take TVLM 513-46546, a brown dwarf no larger than Jupiter but sporting a magnetic field 20,000 times stronger than Earth's. When its field lines snap and reconnect, the resulting flares blast radio waves across the galaxy with the intensity of a miniature quasar. Proving size means nothing when magnetism takes the reins. What fuels these cosmic electromagnets? The answer lies in their turbulent interiors. Unlike stars, where heat smooths out internal motions, brown dwarfs churn like overheated blenders, their convective currents spinning molten layers into a frenzy. This chaos amplifies magnetic fields through dynamo effects, the same process that powers Earth's magnetism, but scaled up to apocalyptic levels. The dwarf 2-mass J10,475,385 plus 2124234 takes it further. Its magnetic field so twisted it acts like a particle accelerator, flinging electrons along corkscrew paths until they scream across the radio spectrum. These aren't just magnetic fields, they're celestial railguns firing charged plasma into the void. The real spectacle begins when these fields interact with the dwarf's atmosphere. Auroras ignite not just at the poles as on Earth or Jupiter, but in sprawling, continent-sized ribbons that writhe across the entire surface. The brown dwarf LSR J 1835 plus 3259 treats the cosmos to a light show that would shame any supernova auroras glowing in X-rays and radio waves, their energy sourced entirely from magnetic violence rather than stellar winds. Imagine the northern lights cranked up to 1,000,000, then set loose to dance across a world without a sun. Yet the most startling twist isn't the strength of these fields, it's their persistence. Stars like our Sun wax and wane in magnetic activity over 11-year cycles, but brown dwarfs cling to their magnetic rage for eons. The object WISEP J190648, 47 plus 401106.8, colder than a winter night on Mars, still crackles with magnetic storms that shouldn't exist at such frigid temperatures. Some theorists suggest quantum effects in their degenerate cores might be at play, where electrons squeezed beyond reason generate magnetism through sheer defiance of classical physics. Others argue these dwarfs are cosmic capacitors, storing energy from their violent youth and releasing it in slow, grudging bursts over billions of years. The implications ripple far beyond the dwarfs themselves. Planets orbiting these magnetic titans would be bathed in relentless radiation, their atmospheres scoured by particle bombardments that make Jupiter's radiation belts look tame. Even rogue planets passing nearby might find their magnetic footprints rewritten by a brown dwarf's invisible hand. And for astronomers, these magnetic monsters are a gift natural laboratories where the extremes of plasma physics unfold on a scale no experiment on Earth could replicate. In the end, these dwarfs prove that magnetism isn't just a sideshow in the cosmos, it's a primal force that can sculpt worlds, ignite skies, and turn failed stars into some of the universe's most electrifying spectacles. Try stuffing a brown dwarf into an astronomical textbook and watch the pages tear themselves apart. These cosmic rebels refuse to sit neatly in any category, shape shifting between star-like and planet-like behaviors so fluidly that even astronomers throw up their hands. One moment, they're launching stellar-scale jets like a miniature supernova. The next, they're brewing methane storms worthy of Jupiter. They're celestial chimeras, part star, part planet, and entirely indifferent to human attempts at labels. Consider their flickering moods. The brown dwarf 2 mass J13,243,553 plus 6,358,281 spends years mimicking a sedate gas giant, its atmosphere laced with methane and ammonia. Then, without warning, it erupts in a magnetic tantrum, belching radio flares that outshine its own thermal glow for hours. Meanwhile, hotter L-dwarfs flaunt silicate clouds more typical of red giant stars, while cooler y-dwarfs like Y0855 shiver at planetary temperatures, their frosty hazes resembling frozen exoplanet atmospheres. Context is everything. Observe one with a radio telescope and it's a frenetic stellar toddler. Point an infrared spectrometer at it and suddenly it's a planetary doppelganger. This identity crisis isn't just academic, it's rewriting cosmic hierarchies. Traditional astronomy divides objects by formation. Stars collapse from gas clouds, planets accrete in disks. But brown dwarfs laugh at such tidy distinctions. Take OTS 44, a young dwarf surrounded by a protoplanetary disk, just like a newborn star, yet at 12 times Jupiter's mass, it's technically too puny for sustained fusion. Is it a failed star-nurturing planet or an overachieving planet masquerading as a star? Even their magnetism mocks conventions. The dwarf TVLM 513,46546 generates star-strength magnetic fields but channels them into planetary-style auroras, lighting up its skies without a stellar wind in sight. Perhaps the ultimate rebellion lies in their social habits. Stars cluster, planets orbit, brown dwarfs, they do both or neither. Some, like the binary system Lumen 16, waltz together like paired stars. Others, like the rogue-wise 1541-2250, drift alone like planets ejected from their systems. Then there's HD 106906b, a brown dwarf parked bizarrely far from its host stars, too distant to have formed like a planet, yet too small to be a stellar sibling. It's as if they've taken a cosmic survey, checked none of the above, and scribbled in their own rules at the bottom. What makes these misfits so invaluable is precisely their defiance. Every time we try to force them into boxes, they reveal the flaws in our categories. Their very existence whispers a humbling truth: the universe doesn't care about our filing systems. Stars, planets, and the wild spectrum between aren't separate chapters, they're a continuum, with brown dwarfs dancing gleefully across every dividing line we draw. And in that dance, they're not just breaking our rules, they're showing us where the rules were wrong all along. Drifting through the void between stars, some brown dwarfs have known nothing but solitude since the day they formed, cosmic hermits untouched by the warmth or chaos of stellar companions. These interstellar orphans, like the infamous Y-8550714, float in perpetual twilight, their only company the faint glow of distant galaxies and the occasional whisper of interstellar dust. Unlike most celestial objects bound by gravity's embrace, these loners exist in a state of profound isolation, their trajectories tracing lonely arcs through the galaxy's emptiest quarters. What's startling isn't just their solitude, it's how normal it seems to be. Surveys suggest free-floating brown dwarfs might outnumber stars in the Milky Way's hinterlands, lurking unseen in the darkness like shadows cast by nothing at all. Take the case of CFBD Sir 21490403, a rogue dwarf drifting unanchored through the AB Doradus moving group. Despite its youth, it shows no signs of ever having been tethered to a star, as if it condensed from a forgotten wisp of gas too meager to form a true stellar nursery. Its atmosphere, rich in methane and ammonia, carries no scars of stellar radiation, just the pristine chemistry of an object that's always been alone. Yet their isolation isn't passive. These dwarfs actively sculpt their own micro-environments. Without a star's heat to vaporize their outer layers, they develop deep, quiescent atmospheres where molecules cluster undisturbed. Some, like the enigmatic Ys 1828 plus 2650, are so cold their water vapor freezes into icy hazes, creating skies filled not with storms but with an eerie, suspended frost. Others might harbor magnetospheres that stretch for millions of miles, invisible cocoons forged by their spinning cores, shielding them from cosmic rays as effectively as a star's solar wind. The most haunting realization: these lonely giants could be time capsules preserving the galaxy's raw ingredients. Stars churn their interiors, recycling primordial elements into new forms, but a rogue brown dwarf's chemistry remains frozen in its birth state. The object SDSS-J 141624, 08 plus 134,826, 7, for instance, shows a deuterium abundance typically seen only in ancient interstellar clouds, a relic of conditions before the first stars lit up. In their seclusion, these dwarfs might be safeguarding secrets about the universe's earliest epochs, secrets that would have been erased anywhere else. What makes their existence so unsettling is the sheer scale of their detachment. While planets orphaned from their stars still bear the scars of their violent ejection-twisted orbits, scorched atmospheres, these primordial loners have always been solitary. They didn't lose companions, they never had them to begin with, and as telescopes peel back more of the galaxy's darkness, one truth becomes clear. For every star blazing in a crowded cluster, there may be a brown dwarf floating light years away, a silent witness to a universe far lonelier than we ever imagined. Peering into the atmosphere of a brown dwarf is like cracking open a cosmic time capsule, one that's been sealed since the dawn of star formation. These failed stars are more than just celestial oddities. They're frozen snapshots of the universe's youth, preserving conditions that vanished from true stars billions of years ago. While massive stars churn and recycle their interiors, erasing clues to their origins, brown dwarfs cool so gradually that their chemical makeup remains eerily unchanged. Take the ancient brown dwarf WISE 1534-1043. Its atmosphere lacks heavy metals, mirroring the pristine gas clouds that existed before generations of supernova polluted the galaxy. Studying it is like analyzing the DNA of the cosmos itself. The real breakthrough comes from their simplicity. Unlike stars, where nuclear fusion scrambles primordial ingredients, brown dwarfs are cosmic refrigerators, their interiors never hot enough to destroy delicate isotopic signatures. Deuterium, a heavy hydrogen isotope abundant in the early universe, survives intact in their atmospheres long after it's burned away in stars. The Object 2 mass J 18,082,002, 5,001,104,378b, for instance, holds deuterium levels so high they match theoretical predictions for the universe's first molecular clouds. It's as if we've found a living relic from an era before planets or even carbon existed. But the time machine effect goes deeper. Brown dwarfs also preserve the violent dynamics of their birth. Their spins, magnetic fields, and even weather patterns encode information about the chaotic nurseries where they formed. The ultra-fast rotator 2 mass J03, 486,022, whirling like a cosmic top, might owe its speed to the gravitational shoves of long-vanished sibling stars, a fossil record of stellar sibling rivalry frozen in motion. Meanwhile, the tangled magnetic fields of dwarfs like TVLM 513,46,546 could reveal how interstellar magnetism shaped the first protostars, back when the universe was filling its first star-forming playbook. The coldest y-dwarfs offer the most tantalizing glimpses into the past. With temperatures rivaling Jupiter's, objects like WISE 08550714 mimic the conditions of the earliest failed stars, those that flickered to life in the universe's first 100 million years, too small to ignite properly. Their sluggish atmospheres, where molecules clump without stellar radiation to break them apart, might mirror the chemistry of the first dark, starless halos that collapsed after the Big Bang. If we could decode their weather, we might finally understand how the first structures in the cosmos gathered themselves out of the void. What makes these cosmic archives so invaluable is their ubiquity. For every shining star, there may be dozens of brown dwarfs drifting unseen, each carrying fragments of the galaxy's history in their dim glow. As telescopes like JWST peer deeper into their frigid atmospheres, we're not just studying failed stars. We're reading the universe's diary, one that's been waiting in the dark for billions of years to be opened. Imagine a future where interstellar travelers don't chart courses to stars. They navigate toward the dim, forgotten giants floating between them. Brown dwarfs, with their bizarre cocktails of hydrogen, methane, and exotic metals, might just become the galaxy's ultimate pit stops. While stars hoard their energy behind walls of searing plasma, and planets lock away resources under layers of rock and ice, these cosmic misfits offer something unique: raw materials suspended in vast, accessible atmospheres, ripe for harvesting by civilizations advanced enough to brave their storms. Take the element lithium, for instance, a crucial ingredient for next-gen fusion reactors and high-capacity batteries. Most stars burn it away early in their lives, but brown dwarfs. Their lithium reservoirs, objects like PSO J318, 522, drifting untethered through space, carry detectable lithium in their atmospheres, untouched by nuclear fusion. For a species mastering the leap between stars, that's like finding an unclaimed oil field in the middle of an interstellar desert. And it's not just lithium. The turbulent skies of warmer L-dwarfs could harbor clouds of vaporized metals like iron and silicates materials that might be mined not with drills, but with atmospheric scoopers skimming the edges of their violent weather systems. The hydrocarbon wealth is even more tantalizing. Cooler T-dwarfs drip with methane and ammonia, while y-dwarfs like Y08550714 might host water ice clouds at temperatures just shy of freezing. These molecules are the building blocks of everything from rocket fuel to synthetic ecosystems. Picture a refinery floating in the upper atmosphere of a brown dwarf, where automated platforms filter methane from the swirling currents like cosmic kelp farms. Unlike planets where resources are buried under gravity wells, these dwarfs offer gases suspended in skyscraping layers, accessible with minimal energy if you can withstand the maelstrom. But the true jackpot could be deuterium-heavy hydrogen, the gold standard for clean fusion power. Brown dwarfs preserve this isotope in their atmospheres like cosmic time capsules, having never ignited the nuclear fires that would have burned it away. A single y-dwarf might hold enough deuterium in its outer layers to power an entire civilization's leap across the galaxy. Harvesting it wouldn't even require landing. Magnetic sails could siphon ionized gas from the upper atmosphere, leaving the dwarf's turbulent depths untouched. Of course, the challenges are as colossal as the rewards. Temperatures swing from molten to cryogenic within vertical miles. Winds scream at hurricane speeds, laced with abrasive silicate or metallic droplets. And then there's the magnetism field so intense they could fry circuitry or wrench apart unshielded ships. Yet for a civilization capable of weathering brown dwarf extremes, these obstacles might be trivial compared to the alternative, mining planets where gravity and geology impose far greater costs in time and energy. The dwarfs' very loneliness could be their greatest asset. Unlike stars whose habitable zones are crowded with competing claims, these solitary giants drift ignored, their resources uncontested. A single rogue brown dwarf, untethered to any star, could serve as a stealth depot, a hidden cache for ships avoiding detection or a way station on routes where stars are scarce. Perhaps the most poetic possibility is that brown dwarfs might already be in use. If advanced civilizations exist beyond Earth, they've likely spotted the same potential. Those erratic radio emissions we detect, they might not just be magnetic tantrums, they could be the hum of machinery tapping into storms of ionized gas, or the beacon of a relay station built by beings who saw these failed stars not as dead ends, but as doors flung wide open. Whether as lithium banks, deuterium wells, or waypoints in the dark, brown dwarfs whisper a promise. In the universe's overlooked corners, the greatest treasures might not glitter. They smolder. Brown dwarfs are the universe's ultimate riddles. Every time we think we've pinned them down, they twist into something new. These cosmic shape-shifters mock our attempts at classification, blurring lines between star and planet so effortlessly that even the sharpest astronomical tools struggle to keep up. Take something as fundamental as temperature. While stars live by predictable cooling curves, brown dwarfs toss the rulebook aside, heating up inexplicably or stubbornly refusing to cool as models predict. The object known as WISE-J 190,648, 47 plus 401,106, 8, for instance, should have been a frigid relic by now, yet it clings to warmth like a celestial procrastinator, as if some hidden engine keeps ticking beneath its surface. Then there's their sheer unpredictability. One brown dwarf might blast the cosmos with erratic radio screams, while its nearly identical neighbor remains eerily silent. Some flaunt storm systems that rage for centuries. Others cloak themselves in patchy, vanishing clouds that defy weather models forged on Jupiter. The dwarf 2-mass J13,243,553 plus 6,358,281 didn't just challenge expectations, it shattered them, dimming by 40% in 5 years without a clear explanation. Was it a global cloud uprising, an atmospheric collapse? The more data we collect, the clearer it becomes. These objects aren't just outliers, they're rewriting physics in real time. Perhaps their greatest trick is how they bridge cosmic scales. A single brown dwarf can host stellar strength magnetic fields while raining planet-like minerals, or spin at breakup speeds while emitting auroras that outshine Jupiter's. They're cosmic Swiss Army knives capable of masquerading as stars in one observation and gas giants in the next. Even their origins are a maze of contradictions. Some form like stars collapsing from isolated gas clouds. Others might arise like planets, coalescing in disks before being ejected into the void. The system HD 106906b, a brown dwarf orbiting impossibly far from its host stars, laughs at both scenarios, fitting neither narrative cleanly. The irony, just as we start to unravel one mystery, another coils tighter. Discover their magnetic fury, and you're left wondering why some retain fields stronger than stars while others go dormant. Map their turbulent weather only to find storms that vanish faster than our telescopes can track. Even their spectral signatures, the fingerprints astronomers rely on, shift over time, turning reliable identification into a moving target. It's as if the universe designed them to keep us perpetually off balance, their very existence a challenge to our craving for order. Yet this chaos isn't frustration, it's inspiration. Every brown dwarf anomaly forces us to reconsider what we know about star formation, planetary climates, even the boundaries of habitability. Could their turbulent magnetic fields seed life on rogue planets? Might their hydrocarbon-rich atmospheres hint at organic chemistry in unexpected places? The questions pile up, but the thrill lies in the chase. For every answer brown dwarfs withhold, they gift us a dozen new paths to explore, proving that sometimes the universe's greatest teachers are the ones that never stop surprising us. From scorching diamond rains to magnetic tantrums powerful enough to outshine stars, brown dwarfs have proven themselves the universe's ultimate rule breakers. These 30 bizarre behaviors, spinning faster than physics should allow, flickering like cosmic strobe lights, even masquerading as planets one day and stars the next, reveal just how creatively nature defies our textbooks. Each discovery peels back another layer of their mystery, their hyperactive auroras untethered from any stellar wind, their rogue atmospheres bleeding into space like celestial ghosts, their ancient chemistries frozen in time since the galaxy's infancy. But the real magic lies in what they represent, not just cosmic oddities, but keys to understanding the universe's hidden diversity. Brown dwarfs are the missing link between stars and planets, a laboratory where the laws of physics twist into strange new shapes. They challenge us to rethink everything from planetary formation to the very definition of a star. And if objects this peculiar exist in our cosmic backyard, what other marvels lurk in the shadows, waiting to upend our assumptions? Perhaps the most humbling lesson these failed stars teach is how much we still don't know. Every telescope pointed at their smoldering glow reveals fresh surprises, proving the cosmos thrives in the gaps between our categories. So keep looking up, because the universe's greatest mysteries rarely shout, they smolder. If unraveling cosmic enigmas like these excites you, don't miss our next dive into the unknown. Hit subscribe and join us as we chase the next big question: what else is hiding in the dark?